For as long as we've looked at the stars, we've dreamed of walking on Mars. But, getting there is really only half the battle. The real challenge, the one some people say is flat out impossible, is getting home. So you might be asking, what's the big deal? I mean, we went to the moon and back, right? We've landed super sophisticated rovers on Mars. So why is a round trip for humans a puzzle that, right now, we just can't seem to solve? Well, that's what we're going to bring see of space travel. Every single thing you want to do, launch, change orbit, head to another planet, land, has a price tag, and you have to pay that price in delta V. And wow, this table really lays out the cost. Just to lift off the Martian surface and get into a stable orbit costs a staggering 4.1 kilometers per second of delta V. Now, to put that in perspective, that is more than twice what it took the Apollo astronauts to get off the moon. Why? Because Mars has much stronger gravity and a fuel will need about 30 tons of oxygen propellant to get home. Because of that gear ratio, hauling all that from Earth would mean launching an extra 300 tons of mass into Earth orbit. It's insane. But if you make that oxygen on Mars instead, look at the savings. You get this incredible leverage, saving a colossal amount of mass. So, all of this points to one, you use the local materials, in this case, the carbon dioxide that makes up almost all of the Martian atmosphere, to create the things you need, like water, breathable air, and most critically, rocket fuel. This isn't some brand new sci-fi idea. People have been working on this for decades. And it all culminated recently with the MOXIE experiment that flew on the Perseverance rover. And guess what? It worked. MOXIE was this little golden box that literally breathed in the Martian air and cranked out pure oxygen. It was a fantastic success, proving the basic idea works on another planet. Okay, so MOXIE worked. Fantastic. But, and this is a huge but, going from a toaster-sized experiment that makes a few grams of oxygen to a full-blown, automated chemical plant that astronauts will literally bet their lives on, well, that's a whole different universe of difficult. So how does it actually work? Well, on paper, the process is pretty elegant. You basically inhale the Martian air, which is mostly carbon dioxide. You compress it and heat it up to incredibly high temperatures. Then you zap it with electricity in a process called electrolysis, which splits the CO2 molecules into pure, breathable oxygen and carbon monoxide, which you just vent away. But here's where reality bites back hard. If the voltage is just slightly off, you can get a buildup of solid carbon, soot basically, that clogs up and destroys the whole system. The fine Martian dust is everywhere and can choke the machinery. And this is all just to make oxygen? If you want methane for fuel, you need hydrogen, which you either have to schlep all the way from Earth or try to mine from Martian ice, which is a whole other unproven technology. And the scariest part? This whole factory has to land itself, set itself up, and run perfectly, all by itself, for more than a year before the astronauts even show up. And to run this factory and, keep the lights on for the astronauts, you need a ton of power. We're talking around 40 kilowatts continuously. That's way more than you can get from solar panels, especially when a planet-wide dust storm hits. The only realistic solution is a nuclear fission reactor, another incredibly complex piece of hardware that also has to land and set itself up completely autonomously. No pressure. And if you want to talk about reliability, get a load of this number. For a mission this long and this critical, the life support and fuel production systems would need what's called a mean time between failure of 14,000 years. Let that sink in. Our absolute best systems today don't even come close. The ones on the space station fail way more often than we predicted. All right, let's imagine for a second we solve all of that. The physics, the logistics, the power, the factory, everything works perfectly. The rocket is sitting on the pad, fueled up and ready to go. We still have maybe the biggest, most daunting barrier of all. The mission itself tries to destroy the crew. Because a trip to Mars isn't just a long drive. It is a sustained, multi-year assault on the human body from every possible angle. You've got constant radiation, the muscle and bone-wasting effects of microgravity, and profound psychological stress from being so completely and utterly isolated. It's a uniquely hostile environment. And the physical cost, it's just brutal. In zero gravity, astronauts lose 1 to 2% of their bone density every month. Their muscles waste away, the fluids in their bodies shift, which can permanently damage their eyesight, and all the while, deep space cosmic rays are zipping through their bodies, damaging their DNA, increasing their lifetime cancer risk, and potentially even harming their brains.
And on top of all that physical breakdown, we can't forget what this does to the human mind. With communication delays up to 24 minutes one way, there's no real-time help from mission control. They are on their own. Studies of people in long-term isolation have identified this thing called the third quarter phenomenon, a dangerous period of depression, irritation, and tension that hits right when the crew is furthest from home, feeling like the mission will never end.
So, wow, when you stack it all up, the physics, the logistics, the insane engineering challenges, the human cost, where does that leave us? Is a Mars return truly impossible, or is it just the hardest problem we've ever decided to tackle? And this is the absolute key to understanding the problem. It's not one thing. It's a cascade of interconnected failures. The physics demands a huge amount of fuel, which forces us to invent an automated factory, which requires a level of reliability we've never achieved, all while the mission itself is actively harming the very people who have to make sure it all works. Each problem makes every other problem exponentially harder to solve.
So is there a silver bullet? Well, a lot of experts think the only way to really break this vicious cycle is to fundamentally change the game with new technology. Nuclear thermal propulsion, for example, is twice as efficient as the best chemical rockets. A leap like that could literally cut the trip time in half. And that would dramatically reduce the crew's exposure to radiation and microgravity, easing the strain on both the people and the machines.
But here's the thing. That kind of tech is probably decades away. And for right now, we have to look at where we really are. Our most ambitious robotic mission, Mars Sample Return, which is just trying to bring back a few kilograms of rocks, is already projected to cost over $11 billion and won't get back here until the 2040s. And that's if everything goes right. Which leaves us with a final, very sobering question about the true monumental scale of what it will take to see human footprints in that red dust and actually bring those humans safely home.